next session on Grundlagen der Videotechnik, Basics of Video Technology. So last time we started with sampling, downsampling an image. This is, for instance, what we have at the color channels. We have this color transform, Y to Z. Y is the luminance, and UAV is the prominence, and UAV are downsampling. But downsampling can be problematic, as we saw last time. So in Python, we do the downsampling using this indexing trick. Basically, we jump the index by n. So it starts with 0, goes to the end, and then after the last column, the capital N, is the step size in which we increase the indices. Right? So here in this case, we only take every nth sample. So in the case of color, this capital N could be, for instance, 2. So every second sample is counted. Or even 4. So what can happen then is shown in this image that we saw later. So first we had those little Python demonstration where we could see what happens when you hold a stripe pattern in front of the camera. And you saw those artificial wavy lines. Remember? So those wavy lines can also be seen in reality. In this case, it's more ray. So in the case of images, this is also called more ray. And here you can see it in this right picture. You see those wavy lines, which are not in the original. So these are an artifact from sampling, which is not on the original. So here we get the original with high sampling rate, many pixels. Here we have a downsampled version, fewer pixels, where you just take every nth sample pixel horizontally and vertically. As a result, you get those wavy lines because you don't know where those sampling points fall. They could fall onto the cement between those bricks, or they can fall onto the grid. And depending on that, you get a bright or a dark spot. And because this grid is not perfectly aligned, it shifts slowly, and you get as a result those wavy lines. So this is what you would like to avoid. So this is not good. So how does our eye does it? And the eye is also sampling basically the image at the point where it has those light sensitive cells, the rods and cones. So basically our eye has the same problem. So you can also see that by looking at the number of nerve fibers coming from the brain. Right? We only have 1 million nerve fibers going from the eye to the brain. But remember, we have about 110 million rods and about 6 million cones. So many more than what goes into the brain. So there must be some compression, some downsampling going on there, right in the retina, before the information goes to the brain using those nerve fibers. Yeah, and when we look at how the retina is built, we can find something that we call receptive feed. Right? The nerve cells go into the retina, and then they branch off and connect to the neighboring sensors, light sensors. So these branching out in this neighborhood is called the receptive feed. Yeah, and the connection is done, as we can see here. So in the center, we have one nerve fiber going to the brain, and then you can see branches out onto the retina to different light-sensitive cells. And they are connected with different weights. So the light-sensitive sensors close to our nerve fiber get high rates. So their inputs get sent to the brain immediately and without attenuation. And when you go a little bit further away, the attenuation becomes higher. So the light that falls into those, it does not count as much anymore. Right? And then what's interesting here, when you continue to go away from the nerve, there's even this negative weight. Right? So there's some point when the light falls onto those cells, then it actually reduces the output of the nerve cell. Right? So it's kind of negative light that you have. It's kind of interesting to observe that this actually leads to a reduction of the impulses sent to the brain, or the information sent to the brain. So that's, here you can see how people measured it. So basically, you shine light on the different parts of this receptive field, and you can see light is turned on. At this point, here's time, light is turned on, light is turned off. And then here you can see the numbers here correspond to the different locations of light-sensitive cells. And in the middle, you have number 3. So you can see here in number 3, when the light is turned on, it has a strong reaction. Right? And that's because it's connected with a high weight. Make sense? So here, basically you have a direct connection to the brain. Then when you shine light on number 2 and 4, you can see when the light is turned on, it actually reduces the activity of the output to the brain. And here you can see when it's dark, it has this kind of constant activity, sending pulses in the medium rate. And then when the light is turned on, it reduces the activity. So this has the effect of a negative weight. When the light shines onto it, it reduces the activity. And then number 5 and number 1, you can see it's not affected because this is outside the receptive field of this nerve. There's no effect because there are no branches going that far. Make sense? So this is kind of the peculiar shape of the receptive field. Yeah, so we have this lateral inhibition. So this is the name given to it. Because when it's lateral, you have this inhibition property. So here you kind of have a schematic top view of what's going on the retina. So here you can imagine you look onto the retina. And here you can see in the center of those dots, you have the nerve cells ending. And the red circles have the positive weights, and then outside those red circles, you have the negative weights. So this is where you have the lateral inhibition. Here, the negative weights. And here you can see that those receptive fields, they overlap. Right? It's not like they're bordering each other, they actually overlap, as you can see here. So when you have a nerve cell, a light-sensitive cell, like in the middle, it goes to both nerve fibers to the brain, but with different weights. For instance, here, closer to the left one, you have a nerve cell which has a positive weight to this nerve cell, and to the other one it has a negative weight. So one light-sensitive cell can have different weights to different nerve fibers. Yeah, so there's overlap. And you can see a diagram of basically flow graph of what's going on in the retinal. This is the flow graph or signal diagram of one receptive field. So it's a little messy here. Can I change it? Yeah. So here in the middle, we have the nerve fiber which goes to the brain. Here on this side, this goes to the brain. And here you have the light sensitive cells, the rods and cones. And the next step is this box with a nonlinear function. So this is basically like a logarithmic function, which means it is doing some sort of compression. So when you have weak light, it has strong gain, so it lets every photon through. But when you have strong light, like from the sunlight, when you have many photons, actually it doesn't increase that much anymore. So you have sort of a saturation like in the logarithmic function. And in this way you can turn the wide range of light intensity, which has many orders of magnitudes, into a much smaller range after the logarithm. And this is important because the nerve cells in our brain and in our retina have only a much lower range of values. Usually it's on the order of a few bits, like 4 bits, so the order of magnitude is much lower, or the range is much lower. So this sort of compression is important, and this then leads to the so-called Weber's law. It should be an A here. I guess it seems I cannot change it. Ja. Das Webersche Gesetz. Weber's law. And this leads to the effect that we see light as a constant addition, where in reality it was an increase by a fixed percentage. Say if we increase the light intensity by 10% each time, then to the eye it looks like we add something constant to it every time. And this is basically the result of this logarithmic function. The logarithm turns the multiplication into an addition. Remember, when you have log of a times b is log of a plus log of b. Remember?
Yes.
Okay, great. So this is basically the effect of this pre-processing, and this leads to so-called Weber's law. Yeah, and after that we have our weights. So the ones, the outputs that are close to our nerve cells in the brain get the high weights here in the middle. Right, so here you can see those weights again. And then we go towards the edge of our receptive field, those weights become lower, and here they even become negative, right, depending on the distance, their location from the center. Right. So here's a reference. Yeah, and you can also see how this kind of curve helps to increase the contrast for edges. Now imagine you have an edge appearing here at this point. Right? To the left you have darkness, small brightness. To the right you have a bright light, bigger brightness. And that means the output, the big brightness, appears mostly at the positive values, and here the negative values, there's not much attenuation coming from it, or not much inhibition, because there's not much light. Right? So this actually increases the visibility of edges. So in this case, this gives us more output as if this left-hand side would also be bright. Can you see that? So here this darkness on this left-hand part means there's less inhibition. And that also means we get a larger output as if this left-hand side would be bright. So if we have a constant brightness, we have less output than here in the presence of an edge. An edge means we have now larger output to the brain. So this is good for object detection because objects usually have edges. They're usually shaped, and for instance you have a bright object in front of a dark background, and this basically allows the brain to see those objects easier because the edges are increased in contrast. So the effect can be seen here. So on top you have a brightness curve, say going from left to right. So on the left hand side you have dark light, then it becomes brighter and then even brighter. And then as a result what the eye is getting is this curve. First it goes down, and this is because now this this main lobe gets less energy or less light, and then on this inhibition part you have bright light. So that reduces the output. And then you get to the part that we just saw, where this inhibition gets less light, and the main, the positive weights get the bright light. Then you have this increase in light, and then basically everything levels out, where the inhibition and the positive weights get the same light. And then we repeat at the next edge. So here you can see this basically increases the difference between dark and bright. It's an increase in contrast around edges. It's kind of an artificial sharpening of the image. Yeah, and here's how it would look like in a test image. So here you can see those different gray stripes. And when you look at the gray stripes, you may notice that they don't look constantly gray, but when you look at the right-hand gray, it looks like the left part of the gray is a little bit brighter than the rest. Can you see that? And when you look at the second gray stripe from the right, you can see that on the right-hand side of the second stripe, it looks a little bit darker than the rest. Can you see that?
Yes.
So this is what actually the retina is doing. This is kind of our processing for the brain. It's not really there because the stripes in itself, they have equal brightness. But it appears to us, to our eye, that we have these different brightnesses. So what it looks like is this. So just before the next brighter stripe, it becomes a little bit darker, and then at the next beginning of the next stripe, it's a little bit brighter. So this is the effect of the lateral inhibition. So in effect, it's kind of like a high-pass filter. High-pass means it increases high frequencies. It's not really a high-pass, but it's more amplifying high frequencies. And this way, improve the visibility of edges. Yeah, you can also see more background information at this link. And when we look at this curve with the lateral inhibition, we see that it has similarity to the sinc function or SI function. Do you all know the sinc or SI function? No? So you should have it in signals and systems. This is like a commonly used function in signals and systems. It's defined like this. The SI function is sine of x divided by x, and the sinc function is quite similar. It's defined as sine of pi x divided by pi x. So the only differ is in this factor pi. And that means they have their zero crossings at different places. So the SI function has zero crossings at multiples of pi, and the sinc function has the zero crossings at integer values, 1, 2, 3, 4. Yeah, and we can also plot it using IPython. So we can start IPython minus pylab. Maybe I can show you. So we just open a terminal. I get it here. And then we just type IPython minus pylab. Did you all try that?
Yeah.
No? So everybody should be familiar with how to start this interactive mode in Python. IPython is simply a little bit more comfortable interface, gives you more functionality for this interface. But it's basically the same as Python. And minus pylab imports matplotlib and numpy. And so this basically makes it look like MATLAB, for instance, or Octave. So then we have this interactive interface, and you can define your x values. And here I define the x values as a lin space ranging from minus 2 pi to plus 2 pi in 100 steps. And so here, paste it. Here I have my x space. And here you can see it indeed goes from minus 2 pi to plus 2 pi. Remember, 2 pi is 6.28, right? And I have 100 values within this range. And I use that to plot the SI function that you can see here. So here plot, I use the x values for the x-axis, and for the y-axis I use sine of x divided by x, which is the SI function. So let's copy it. Copy and paste. And here you go. Here we have our SI function. Practical, huh? So in this way we can easily plot, and you also have practical functions here. You can save this plot, or you can zoom in. So here you can make a rectangle to zoom in. For instance, if you want to find out where the zero crossing is. So here you have the zero crossing, should be 3.14, minus 3.14. Yeah, I guess it fits. Or here you go back to the original form. Yeah, so you should be all familiar with this. So this is our SI function. And this SI function has special properties in the so-called discrete Fourier transformation, or DFT for short, or also in general the Fourier transform in the non-discrete. Have you heard about the Fourier transform?
Yeah.
Yeah, Sensistivity. Have you heard about the discrete Fourier transform?
Okay.
Not yet. Okay. So this is now the discrete Fourier transform. So we have seen it in the case of aliasing or array in the image. The number of brightness oscillation per degree is important. Right? If we have a fine pattern, we get those array or aliasing. Right? We only get this problem if we have a very fine pattern. Otherwise, the sampling point doesn't matter. Sampling width. If you have a very smooth image, then a slight shift in the grid doesn't matter. But if you have a fine pattern, the small shift in the sampling rate makes a big difference, and that causes aliasing or array. Yeah, so therefore it would be helpful if we could present our image or signal by a sum of different sinusoidal functions of different frequencies. So this allows us to use the discrete Fourier transform. I should say you can do this. We obtain this by using the discrete Fourier transform. So we start from our signal x, which can be the intensity values, the luminance, along the line of our picture, or also, for instance, the samples of an audio signals, of an audio signal having a number or length of n values in the range of 0 to n minus 1. So then the DFT is defined as this sum. So we see we have a sum over n values. N is our signal length, for instance, the length of our row or the length of our audio signal. And here we can see now we have a new variable k. Right? So the sum goes over n values using this exponential coefficient here. This exponential coefficient is basically very similar to the Fourier transform, except that now we have this small n and this capital N here. And this small n is integer because this is now a sum. Remember, in the case of the Fourier transform, we have an integral. Now we have the sum because we have samples. It's not time continuous, but time discrete. Hence we have a sum instead of an integral. And that means here our time variable t is now replaced by this integer sample value n. So n can be 0, 1, and so on. And it divides by the total number of samples. So basically our t value goes from 0 to 1 in steps of 1/n. Yeah, so then as a result we get k frequency coefficients, and k is between 0 and n minus 1. So if k equals 0, that means we have the lowest frequency, constant, no change. If we have k equals n minus 1, that's the highest possible frequency that we can represent with this sampling rate. And we also have the inverse DFT. Fortunately, we can inverse transform it. And this is basically, again, a weighted sum, but now of oscillations representing the origin signal. So here we have the coefficients that we just computed. Each coefficient is multiplied by its corresponding exponential frequency function here. And then we sum up all those frequencies and we have this factor of 1 of n in front of it. And remember that e to the j omega is simply, according to Euler, is simply cosine of omega plus j sine of omega. Right? So this is an important part of the equation. The exponential function can be written as two sinusoidal functions. Cosine of omega for the real part, j sine omega as the imaginary part. Makes sense? So you all have seen this equation 3 before? Okay, good. So this shows you that we can rewrite our signal, the luminance signal or also some audio signal, as a sum, a weighted sum of oscillations, cosine and sine oscillations. Right? So that means we have low frequencies and we have high frequencies with different strengths, and the strength is given by the coefficients x. So this can now be used to analyze our image. because then we can take a look at those xk for the high frequencies. So if we have high values for high frequencies, that means we have a problem with aliasing. If we have very low values or disappearing values, xk for high frequencies, that means we have no problem doing the sampling. Because only at high frequencies we will have a problem. Yeah, and these coefficients are usually complex valued. Right? The xk are complex valued. And that basically has the effect that we can introduce phase shifts for oscillation. Remember, we have a complex oscillation, the e to the j omega, and then we have a complex factor, and that means this complex factor again is something like e to the j phi, right? And then basically e to the j phi times e to the j omega something. Then we can unify it and just have plus phi in the exponent. Right? So that means we just have a phase shift. Yeah, so the inverse describes every signal as a sum of weighted cosine and sine oscillation at different frequencies. So every signal, even if it doesn't look like a sine or cosine wave, can be represented by the sum. And fortunately, there are fast and very efficient algorithms for calculating the DFT and the inverse DFT, and they are called the fast Fourier transform, or in short, FFT. Right? And the FFT is actually an invention which made digital signal processing practical because it reduces the complexity a lot. And in Python, we have it included in the package numpy.fft. Okay, so fortunately, we don't need to program it ourselves. It's already available in Python as in this package. So here's an example. Maybe I can also try it here. We already have our IPython window open. So I just make this test signal here, which is just the sine of a sine wave, which means, yeah, what kind of function is this? We have to guess. How will this function look like?
Sine.
No. It is a sine, S-I-G-N, of a S-I-N sine. So what's the result? So the sine looks like this, goes up and down. Right? So how does the S-I-G-N look like? Do you know what S-I-G-N means? Yeah?
It means that you take the sign of the values, the plus or minus, or 0 in case it's 0. And for the sine function, this means that we're going to have a function that looks like a positive box for the part where the sinus function is positive, and the box, the negative area, where the sine function is negative.
Right. So this SIGN function returns a plus 1 if you have a positive sign. It returns a minus 1 if you have a negative sign. And it returns a 0 if we have exactly 0. So mainly we have just plus and minus because there are not many places with 0. So we can try it now in Python. So going back to our IPython window. Oh. Copy. There you go. So now plot of x. So you can see how it looks like. So is this what you expected? So you can see it's plus 1, where the sign is positive, and it's negative 1, where the sign is negative. Maybe you can simply plot the sine function on top of it. Fortunately, it's very simple in Python. plot, paste. See, now you have both of them on top of each other. Can you see it?
Mhm.
So it simply took the sign, the SIGN of our sine wave, and returned plus or minus, or 0 if we have a 0 crossing. So this is kind of a test function which we would have if we have a bright line or you know, bright line basically followed by a pitch black all of a sudden. Okay, so bright, dark. Low gradual transition. There's pretty abrupt transition between bright and dark here in the middle. So, and this is actually what introduces high frequencies. This sudden jump means we have a strong rate or high rate of change. And this high rate of change is characteristic for high frequencies. Right? So now we can see how many high frequencies we have if we apply our DFT to this signal. So this is in the next line. So here, actually you can see our sine function. So you have 0 in the beginning, then 1, 1, 1, 1, and then minus 1, minus 1, minus 1. Right? So a sudden change here. And now we apply the FFT. So I don't need to specify numpy because that's already imported in the namespace of IPython. Copy. Paste. So now I have an x, and here we can take a look at the x. So this is now the result. So here's the first x. This is x of k equals 0. Right? We have 1 plus 0 times j. And here, this is x of k equals 1, the next one. You can see we have minus 1 plus minus 4.8 times j. And here x of k equals 2, we have 1 plus j, and so on. So you can see these are complex factors. So fixed complex factors. One for each frequency coefficient k. So here you can see the result again. And now we can also apply the inverse FFT here. Okay. And this is the result. So why do we now have complex factors after the inverse FFT? No?
I think it's because we're using numeric calculations, so there is some slight lack of precision sometimes.
Yeah.
And whenever this occurs, we get some complex values, but the imaginary part is really small. It's 10 to the minus 16th power, so
Right.
it's negligible.
Yeah. Very good. So these are basically rounding errors that we get. Python uses, I think, 16 digits. So that's why we get an error in the order of 10 to the minus 16. And so this is the limit of the computation accuracy of Python. And in general, you could have complex signals. Right? The FFT can use complex signals as the input. It doesn't have to be real input. It can be complex. And hence also the inverse FFT should be able to produce complex numbers. Right? So this is actually correct. In general, we should expect complex numbers also after the inverse FFT. It's just that in our case, we have real values as the input. And hence we also expect real values at the output. But because of the limited accuracy, it's still the type complex. So sometimes this creates problems in your software, and then it's useful to simply apply the real part. So we can apply, I think it's real. So let me say real. Yeah. See, this is now the type float again. It's not the type complex, and often in your software you want to continue to use the type float and not complex. And then this basically catches this case of complex numbers with very small imaginary part. Make sense? So here you can see the imaginary part is now dropped, and you can also see the first entry instead of 0 is something 10 to the minus 17. So again, the same effect, it's a rounding error. Okay. Yeah, so this is what I just did. Yeah, and also note that the coefficients are symmetrical about the center. So we can take a look again. When we look at those coefficients here, you can see the first two are basically here, this one and this one is conjugate complex. Right. Where's the center? So we have 1, 2, 3, 4, 8 entries. This is 0. Then the fourth entry corresponds to the Nyquist frequency. And so which would be 0, 1, 2, 3, 4, this one here, which is identical to DC. And then everything is symmetric around this point. Conjugate symmetric. So here we have an entry which is conjugate symmetric to this one. So you can see it's just the negative imaginary part, but the same number. Then if you continue here, this is the same number as this one, just with the opposite sign for the imaginary part. So here, index k equals 4 is the symmetry center. Right? And when you go to the right, you get a number. When you go to the left, you get the same number, except that it's conjugate complex. Can you see it? So there's always this symmetry around k equals n. And that's what you always get when you have real valued signals as the input of the FFT. And so this is the peculiarity of real valued inputs. Yeah, and we can also easily see where this symmetry comes from by looking at the sinusoidal oscillations of the FFT. For the frequencies, for instance, k equals 1 and k equals 7. Right? So they should be symmetric. This is one of the symmetric pairs. So they're symmetric around the center k equals 4. So in IPython, we can plot the two. Here you can see I use k equals 1, and here you can see I use k equals 7. So these are basically the sine function of this exponential function of the DFT. So here we have this 2 pi over n, right? Capital N was 8, and we have 2 pi, then we have times k, and times n. So this range here is the small n going from 0 to 8, excluding 8. And number 1 and number 7 was the index k. So we compare it to the exponential function that the DFT uses. Here we are. See, I just implemented this piece here. 2 pi over n, so this was n, capital N equals 8. then small n is this range, 0, 8, and then this k is specified as either 1 or 7. Right? And we just look at this sine part. So here you can see it. And here you can see it's indeed identical, except that the sign is flipped. Right. So this is actually what we observed. So we can see here k equals 7, and that's actually identical to k equals minus 1, because the sign here is periodic. So 8 is the same as 0, and that means 8 minus 1 is the same as minus 1 for the frequency index. And minus 1 means minus sign of blah 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 times 1. Right. If you change the sign of the argument of the sign, you change the sign of the function. Sign of x is minus sign of minus x. Makes sense? So that's why we observed it here. And we could do the same with the corresponding cosine functions, and they would be identical for those frequencies index. So the real part doesn't change, but the imaginary part changes sign. So this would be sinusoidal oscillations for the imaginary part of the DFT. And the cosines are for the real part will be identical. Yeah, and the highest frequency is k equals 4. And we can also see that in IPython by just taking this example, cosine 2 pi over 8 times k equals 4 times this range for the n value, and then plot it. So here you can see the result. It just goes up and down. So this is the cosine function for k equals 4, which is basically the Nyquist frequency. And you can see it just jumps from +1 to -1, back to +1, and so on. So it simply changes the sign for every other sample. And this is the maximum rate of change that we can obtain for real valued signal. Right? We cannot change faster than from one sample to the next. And hence, this is the highest possible frequency that we have with this sampling rate, our Nyquist frequency. Does it make sense? So now imagine we have twice as high frequency as this Nyquist frequency. How would it look like?
In 16?
No, I mean, we have the same number of samples, but now we have twice as high frequency. So k, basically,
K will increase.
k equals 8. How would it look like? So this is k equals 4. How would k?
8. Because
Yeah, so how would this plot look like then?
There are going to be 16 triangles.
Right, imagine, but observe, we can only see the value at the sampling points. Right? So for k equals 8, it should go from 1 to -1 at 0.5, and then up to 1 at 1. But we don't know or don't see the 0.5 because we are not sampling there. Right? So that means we only sample this function at the point where it's +1. We don't even see that it was -1 in between. Make sense? So when we go to k equals 8, then we have a constant sequence of 1s. It looks the same as DC. There's no change at all. DC for direct current, remember. And this basically is also part of the symmetry. Around Nyquist, there is this symmetry. So we go up to Nyquist, and then if we increase our frequency, we go down again. And this is this effect, right? If we are going up all the way to n equals 8, we are down at DC again. And go up and down. Make sense? So this is basically part of sampling. The maximum rate of change we can get with a given sampling rate is Nyquist. Where we have one sample plus, the next sample minus, and so on. If you try to do this faster, then basically in effect we go down in frequency. Yeah, that's part of the symmetry that we observed. Yeah, now I have a little Python example here, real-time Python example of a microphone signal. Here, this little program, and it uses blocks of 1024 samples. So capital N in this case would be 1024. And the FFT is applied to each of those blocks, and then the magnitude of the coefficients. Remember, we have complex value coefficients, so we can take the magnitude. What's the magnitude of a complex value? Remember?
It's the square root of the square of its real and imaginary part somehow.
Remember, everybody? So it's real part squared plus imaginary part squared and the square root out of it. So this is then plotted because it's easier to show on a window, right? Or on a plot. It's easier to plot one value instead of two values. So now we can plot, well, let me first open it in the editor. Copy. And quit my, so this is how I quit it, like a function. And, oops. Gedit. So this is this little program, and this is also available to you in Moodle 2. So if you look at the program files for this lecture, you will find it. And here you can see what it does. First it imports Pi Audio, because Pi Audio is used to access the sound card. Does everybody know Pi Audio? Who doesn't know Pi Audio? Okay. So maybe I should explain it a little bit. So the rest basically should be familiar. I use NumPy as NP, then Matplotlib as PLT, Matplotlib animation as animation. So I actually make an animated plot. And here I define a chunk size or block size of samples which are read from the sound card. And the width is 2 bytes per sample. This is the standard audio format. 16-bit per sample or 2 bytes. Right. So this is what I'm using. And I'm using mono, which is 1 channel, at a sampling rate of 32,000 hertz. It's also kind of standard. It's a little lower than CD sampling rate, which is 44,100. Here I'm using 32,000. And I'm recording for 70 seconds. So here I'm then defining the FFT length, which is only half the size which I'm reading from the sound card. And this is a trick to make this run in real time, even on slow computers. So it doesn't have to be. Then I'm setting up the plot. And here I'm setting up the animation function for the plot. And here you can see it reads from the audio card. So stream is basically the object for the audio card, and read is the function in it which reads from the audio card this number of samples, chunk, which is 2048. So then we have in data an array of 2-byte samples. So here 2 bytes each. And this is then converted into short integers using the function unpack from the library struct. So this contains the hexadecimal values into data, from data into short integers. And here this is the conversion format from where it will convert. Data is our binary array. And then I convert the short integers into floats in this float here. So samples now contains the samples as float values, and float is easiest to compute with, and that's why I did this conversion. Make sense so far? Do you know this struct library? No? You can see struct here. This is imported, import struct. This is a Python library, and this is basically to handle binary arrays. This is basically containing those conversion functions. So what you get from the sound card is not standard integer values, it's just binaries. And to make it an integer that you can compute with, you have to use those conversion functions like unpack. So basically just a conversion. Here I'm then computing the FFT. You can see FFT of the samples of the size of FFT length. Here I do some normalization, which is not really important. Here I'm taking the magnitude of it. So this is actually doing the squares of real and imaginary part and the square root. And then I turn it into a dB value here, 20 times log. And so this is the dB value for voltage. And we assume that we get voltages from the sound card. Again here, normalization to make this log a log of base 10. So log in general is a log of base E. And you turn a log of base E in by dividing this log of by this log of 10. So this is kind of a trick to get a different base.
What is this ABS?
Absolute. So that means I take the magnitude. ABS means magnitude. Absolute means absolute value. So if you have plus minus here something, then it removes the minus. And if you have complex numbers, it produces the magnitude. Meaning real squared plus imaginary squared, taking the square root out of it. Right. Does the log stuff make sense to you? So in effect, I have the log base 10 here, and I plot it. So this is basically the dB values. So then I define this callback function, or this animate function. And here I come to the main part. Here I'm setting up the audio card. High audio, high audio. P is then the pointer to the audio card. Here I'm displaying the number of devices found. And then stream opens my audio card and it produces a new object here. Stream is a new object and it's produced from this pointer P with the argument of all the values that we use for setup. So here, 2 bytes per sample, mono, 32 kilohertz, input is true, output is true, and then frames per buffer, so we have 2048 samples. Yeah, and then we basically start the animation function here to basically continuously get the input from the microphone and display the resulting magnitude FFT values as dB in our plot. And yeah, more questions to this program? So now you also know how to access the microphone from the sound card using Pi audio. This can also be quite handy. So then let me execute it. F7. See, now you can see the live magnitude FFT in dB. So you can see horizontally is the K index. K in this case goes from 0 to what index?
K.
Huh?
K.
Yeah, what's the highest index for K in this case? It's not 8.
4.
What's the FFT length, remember? The FFT length was 1024. This is how I set it in the program. So if the FFT length is 1024, that means capital N is 1024. And the length is equal to capital N, because that's the number of samples that we deal with. Right? Remember, the number of samples for the FFT was capital N, and this is also called the FFT length. So what's the maximum key K here? Index, the K index?
1000.
Huh? 1000? More. Yeah.
It's 1024.
No.
323, 1023.
Yes, right. 1023. So if the length is n equals 1024, the maximum k was n minus 1. Remember, it goes from 0 to n minus 1. So total we have 1024 samples, but since the lowest index is 0, the maximum index must be n minus 1. So here, the k goes from 0 to 1023. Yeah, and you can also see the symmetry around the center. So we have Nyquist. So which index is Nyquist here? Nyquist frequency? Remember the maximum possible frequency that we can represent with the sampling grid? So what's the Nyquist frequency here? Or the index which represents the Nyquist frequency? Well, remember our previous example. Capital N was 8, Nyquist was 4. Right. Now we have capital N is 1024. 512. Exactly. So it's always half. And that's why it appears in the middle. Right. So we have the symmetry around the middle, because that's where the Nyquist frequency is. This is the maximum frequency that we can represent with the sampling grid. So you can nicely see the symmetry around the center. So here's the center, and it's always symmetric around the center. So basically, when we go to the upper limit here, 1024 would be identical to DC again. And that's also why we are not computing it. Right? We are not computing k equals 1024 because that's identical to k equals 0. We cannot distinguish it from k equals 0. Yeah, and here, that means here to the left side, we have the low frequencies, starting from 0 and then going up. And the same on the right-hand side. Low frequencies going down means higher frequencies. So to see those frequencies, I could now whistle. So when I whistle and go higher in my tone, whistling tone, you should see peaks coming from the sides going to the center. So let me try. Can you see it? Nice peaks, huh? So my whistling is not a perfect sinusoid, but it was clean enough that you could see it as a clear peak. And also it shows you when the tone becomes higher, you move towards the center from both sides. Okay. So I can close it. Which means n equals 1024. Also called NFT size. Yeah, maybe that makes it clearer, since you had trouble understanding what the K means. Does it help you? And the highest possible frequency is like this. Which appears in the middle. And index k equals n over 2 equals 512. Like this. So remember the meaning of Nyquist frequency. Yeah, so we saw the symmetry, and when whistling, we see the larger coefficients at the corresponding frequency index. Right. So I just mentioned that. Yeah, we can also represent the magnitude of the DFT coefficients as different colors. On the x-axis, the first half of the DFT coefficients such that the coefficients with the lowest frequencies are on the left and those with the highest frequencies on the right. And you plot time on the y-axis. Then, oops. Then we get a so-called waterfall line. To include time. We represent the magnitude as different colors. frequency on the x-axis, on the y-axis we have time, and then the color gives us the magnitude of the DFT coefficients. So we can see it here in this program, which I'm opening now. Copy. Gedit. So here the beginning is the same, but now we include CV2 for live displaying. It's this color image. And here the setup of the audio part is the same. But now we have a slightly modified main loop. Here I have an infinite while loop. I'm reading the data again the same way as before. Here now I'm also computing the FFT the same as before, but now I'm assigning those magnitude values to an R channel, R for red. So here this goes to the red frames, the red primary color of our frame, and then I'm computing the green values as the magnitude of 1 minus 2R, so some nonlinear function, and then the blue function as 1 minus red. So two nonlinear functions to turn the magnitude into different colors, basically. And then here, in this row here, I'm using imshow to display the resulting frame. And to make it time dependent, I shift the rows one up for each time I run this while loop. So here you can see the higher frames get the let's see here, the higher frames get the lower frames, and then this last, the lower frame gets the new values here assigned. Right? So frame of rows means the lowermost row of our frame gets the new values, and the previous ones are shifted up. So in this way we have a reverse waterfall, it goes up. So did you use imshow before? Who knows imshow? Who doesn't know imshow? Oh no. So basically it's just, as I show here, imshow expects, if it's color, it expects a tensor of 3 dimensions. So you can see the dimensions here. So first is the row index, second is the column index, and then the last is the primary color index. So, as you can see here. So, in this case, I'm always assigning the lowest row the output of the FFT, which is an array of length 512 in this case. Yeah. Because I'm only using the first half, because I know that the upper half is symmetric, so I can simply drop it. So I'm only plotting the lower half of this FFT, which you can see here. So here I have the same FFT, the FFT length FFT, but I'm only keeping the lower half here, from 0 to FFT length over 2. Right? And I'm using the int here, the typecasting to int to avoid an error message. Make sense? So I'm only going from 0 to Nyquist in this case. So okay, let me try Python. Okay, here you go. So here now you can see the result. On the left hand side, you have the lowest frequencies. On the right hand side, you have k equals 512, the Nyquist frequency. And then it's shifted up. And then the colors represent different magnitudes. So yellow means highest magnitude, then reddish, lower, and then bluish means the lowest magnitude. So you can see here on the left-hand side, I indeed have the highest magnitudes. That's where I'm speaking, actually. And then towards higher frequencies, there's not too much going on. So now I can whistle again. Nice, no? So here you can see this wavy line, and you can also see the first harmonics. See, there's this copy a little bit to the right. So this is the first harmonic of my whistling. So twice the frequency. Can you see it? Yeah. So you can also see when I'm whistling higher, it goes to the right, and then it goes back. So it's indeed a nice frequency decomposition in this. And you also, in this way, you have the time dimension, which is important, for instance, for analyzing speech. So as you can see here, like A, E, O. Can you see the differences? So this is how speech looks like in this spectrogram. Right? And this way you can actually also analyze speech. And this representation is also used for speech recognition. Okay, so when you have speech recognizers, this is usually the first step, the pre-processing step. And then you apply neural networks to it to then recognize certain sounds, certain vowels, or certain words. Yeah, and I end this by clicking Q, the key Q. Here you can see on the last line, I'm waiting for the key Q to be pressed. Right? So here, wait key returns the ASCII code of the key I'm pressing. And if this ASCII code corresponds to the key Q, then I break this infinite line. So just hit the key Q and then it stops. So again, this is in Moodle, so you should try it at home with your voice and with whistling as I just did. Okay. Observe. So this is still part of some machine translation, so sometimes it looks a little bit odd. Yeah, so we can also use this FFT and apply it to images, right? But there we have rows and columns. So what we do is first we apply it to each row and then to each column. So there should be a row. Yeah, and there's actually a function in Python called FFT2, which does this for you. So it's actually not very difficult, but there's a function which automatically does this. So FFT2. Yeah, so we can calculate the true DFFT for each frame, for instance, of the green component of our videos. Just as an example. So here, for instance, and we can display this video in a window and use the magnitude. This translation sometimes is really terrible. Sorry about that. So again, we apply abs, the abs function. And here you have this Python script. It's actually fairly short. Here we again use CV2. So we just saw CV2, we use the same here. But now we also use it to capture from the webcam or the video cam in our laptop. So here this first line sets up an object, cap, which is connected to the video capture device of our laptop. And then again we have this infinite for loop. And here in the function read from the object cap, we can access one frame. So we read in one frame, and we have a return value here, which is basically a binary value which tells us if the reading was successful. So frame is now this three-dimensional tensor, rows times columns and times primary column. And here we can now apply the FFT two-dimensional to the green component, which has the index 1 in the primary column index. So here, two-dimensional function from the green component. I normalize it to be between 0 and 1, and also turn it into a float in this way. Then I apply the FFT2, normalize it by this vector 512, and then I just show it. Right? Here with imshow, as we just did. So the rest is basically the same, and after I'm done, I'm releasing the window. So we can start it with Python video rec disk, FFT disk. So try. Yeah. So here you can now see the result. Can you see the corners here?
Yeah.
That means you have each corner means the lowest frequencies horizontally and vertically. So here horizontally, it shows the horizontal frequencies. Again, because of the symmetry around the center, you have the lowest frequencies on both corners. Same is true for the vertical frequencies. Here on the vertical axis, you have the vertical frequencies. And again, you see the largest values on the ends, which means we have low frequencies with the highest energy, or the highest magnitude. Does it make sense to you? So now I can also generate larger frequencies by using my test plot here. Here's the test plot, here we go. So here I have some larger frequencies, right? And I hold it forward. Here you can see those additional dots. So now we have high horizontal frequencies, which means if I go from left to right or horizontally, I have many changes in brightness. So when I'm going closer, it appears as lower frequencies, less abrupt changes, less fast changes. If I go further away, you get higher and higher frequencies. If I turn it vertically, it's the same for the vertical axis. Can you see it?
Yeah.
Or diagonally. Right, so now I have this frequency axis, strongest, and correspondingly you see those bright dots. And those bright dots, the location of those bright dots corresponds to the frequency that we see along this axis. So this is the spatial frequency that we observe here in this diagram. So it actually indeed tells us what frequency component are present in our picture. So when we go further away, we get higher frequencies. And here, even higher frequencies. Nice one. So this shows you what frequencies are present in our image. And the location of those dots show you which frequencies are present, and the brightness of those dots tells you how strong those frequencies are in the picture. Yeah.
So a dot closer to the center of the image means there is some higher frequency, and as we go further to the edges, it represents lower frequencies.
Yes.
Is it? Okay.
Yes. Correct. So here in the edges, we have the lowest frequencies horizontally and vertically. In the center, we have the highest frequencies horizontally and vertically. So what's special here compared to audio is that we have different directions. Right? We not just have frequency, we also have to know if it's horizontally or vertically. Right? We have two dimensions. So this additional dimension is now new for images. Otherwise, mathematically, it's the same as for audio, which has just one dimension. Here we just have another dimension, and 2 dimension. Here again, quit with Q. So again, we can see here what I just showed you. The location, it shows us the spatial frequency, and then the strength of the brightness gives you the strength. Yeah, and interestingly, this image still contains all the energy, all the information of the original, because we have the inverse FFT, but except it also needs the phase, right? So magnitude plus the phase, which I didn't show here, allows us to reconstruct the original image just from this. Right? And remarkably here was that unlike the original image, most dots were black, right? Most were zeros. So basically, if you just concentrate on the bright spot of the image, this would allow us to reconstruct the original image mostly with only a small error. And since those regions are very small, this also shows us how we can compress. We're concentrating on those regions which actually are most active. Yeah. Okay, but I guess time's up. So thanks for your attention and have a nice rest of the day.